Hi, thanks for watching, and today I want to describe Newton's method and also prove a cool error squared convergence rate theorem. So what is Newton's method? Suppose you have a function f and it has some 0 at x star. The way it works, I'm not a programmer, but basically you start with the initial point x naught, and the idea is, because the tangent line is so close to the function itself, maybe to find the 0 of the function, you should just find the 0 of the tangent line. So suppose you have this tangent line, so tangent line at x0, and the idea is, well, the y-intercept of that tangent line, let's call it x1, should be pretty close to actual 0. And let's just figure out what this means mathematically, where the tangent line at x0, well, what's the definition? Well, it goes through the point x0 f of x0, and the important thing about tangent lines is that the slope of that tangent line is f prime of x0. So the equation then becomes y minus f of x0 equals to f prime of x0 times x minus x0. And the point is, as I said, the 0 of this function is roughly the y-intercept of that, it's roughly the, the y-intercept, no, it's roughly the x-intercept of that tangent line, meaning that we said y equals to 0. So if this is 0, we get 0 minus f of x0 equals to f prime of x0 times x minus x0. And now let's just solve for that, and we get, again, a minus f of x0, divide this by f prime of x0, assuming it's not 0, and then x minus x0. And so in particular, x equals to x0 minus f of x0 divided by f prime of x0. So in other words, this x1 is just given by this formula. So x1 is x0 minus f of x0 divided by f prime of x0. But here's the question though, what if x1 does not give you the 0? Well, it's not a problem, you just continue. So suppose you have x1, you use this as your new x0, you find that tangent line at x1, and then its x-intercept gives you a new point x2, and the point x2, you can just find it using a similar formula. So x2 would be x1 minus f of x1 over f prime of x1. And indeed, you can repeat this algorithm more and more, and in fact, what you get is that the next term is always given by this formula of the previous term. So in general, xn plus 1 equals to xn minus f of xn over f prime of xn. Now, I'm not an applied mathematician, but if I were, I would show you cool code and show that, it does sort of converge, at least in this picture. But I know a fellow mathematician who knows Python, so maybe he can do that. Anyway, the question though is, and here's the interesting thing, does this converge? In fact, not always. You can even have a cool situation like that. Hopefully it's correct, but suppose you start with this point, like x0, then you find the intercept of the tangent line, x1. It could happen that if you take this tangent line, you would again get that the intercept is x0. So it could get that x2, the intercept of that tangent line, equals to x0, which is a problem because then it just cycles back and forth. x3 would be x1, x4 would be x2, and then in this case, clearly there's no convergence. And in fact, it's not always clear when it converges, but I want to show you something really cool. Namely, if it indeed does converge, then we actually get super fast convergence. In other words, the rate of convergence of this method is quadratic. So if, let's say, your initial guess is just 0.1 off by your actual guess answer, then the next term will be like square of that. So we have like 0.001 or something of that. So it's really cool. So here's my claim. Okay. So suppose you have a function, I guess twice differentiable, whose derivatives are continuous. Again, we'll sweep this under the rug, but suppose there is actually a solution. So suppose there is x star in AB with f of x star equals to 0. Of course, if there's no 0 of this function, there's no hope that this algorithm would work, right? So suppose here f has a root, and that root satisfies that the derivative of that root is non-zero. Otherwise, we might have problems where the tangent line is almost horizontal, and we also don't want that. Then, what I'm going to show, if actually you're really close to the solution, then if xn is close enough to, so suppose your iteration is actually very close enough to x star, and define the error epsilon n to be just the difference between your iterate and your root, okay? And think of it as the error. Then I'm going to show you that the error in the next iterate is actually much, much smaller. Then epsilon to the n plus 1 is less than or equal to m times epsilon squared. In other words, suppose this is x star and we found xn. And suppose, again, hand wavy, this is close enough, then xn plus 1, again, if this is the error, epsilon n, then xn plus 1 is much closer to x star. It's like quadratically closer. And again, that's good if this is small. And in case you're wondering what is m, m is just any constant bigger than f double prime at x star divided by f prime of x star. Actually with a 2. Okay, and let me show this. So it has quadratic convergence. Excellent. I think there's some schemes even have exponential convergence. So this is really, really cool. But the reason I like it is the proof. So what is the proof? It follows from Taylor expansion. So suppose you have this number f of x star, then Taylor expanded up to the first order. So f of xn plus f prime of xn, x star minus xn, plus a remainder, and you can write the remainder in the following form, namely it equals to x star minus xn squared times a number, and that number, it can be written in terms of f double prime. So it's f double prime of xi n, where xi n is between xn and x star. So at least in this picture, if you have xn and your true solution x star, xi n is in between, and it follows from the mean value theorem. So in fact, you can write open interval. That's fine. And by the way, if you want to see a proof of Taylor's theorem, there's an amazing one I'll either have put already or will put it soon. Okay, so what do we know? We know this. So again, we don't even need this thing. We know that f of x star can be written in terms of, at least first order Taylor expansion. But what is f of x star? Remember, x star is the 0 of f. So that equals to 0. So 0 equals to f of xn plus f prime of xn times x star minus xn plus f double prime of xi n of x star minus xn squared. And now take this equation and divide it by f prime of xn. So 0 over f prime of xn is not a problem. This you divide by f prime of xn. This you divide by f prime of xn. This you divide by f prime of xn. And I forgot, sorry, 1/2. Okay, very good. And now, right, f prime of xn over f prime of xn, that's 1. And we sort of want, xn plus 1 to appear. So, if you remember, what was xn plus 1? That's xn minus f of xn divided by f prime of xn. Well, that's very good. We have this thing. Let's just put it on the right-hand side. So, minus f of xn over f prime of xn equals to x star minus xn plus 1/2 f double prime of xi n over f prime of xn x star minus xn squared. Alright, and now we can do more than that. We can put this xn on the left-hand side. So xn minus this equals to minus x star, minus x star equals to that. Right. So in other words, this term equals to some constant times the error squared, so it's pretty good. And now, as I said, we want to write this in terms of xn plus 1. So this becomes simply xn plus 1. This is just x star. And that's 1/2 f double prime of xi n over f prime of xn x star minus xn squared. Okay, as I said, we want to deal with errors, so let's just put absolute values everywhere. And I guess here also absolute. Doesn't matter, it's a square, but we have this. Now, this thing, remember I called this epsilon n plus 1. And that equals to 1/2 f double prime of xi n over f prime of xn. And that's just epsilon n squared. And we're almost done because here's the idea. We want to use this constant m. That m, it involves f double prime, but at xn. But it's not a huge deal, and I'm going to sweep this under the rug a little bit. But remember, what was x star? What was xi n? It was a number between xn and x star. So the idea is, if xn is close enough to x star, this little thing, it's very small, so in particular, xi n is very close to xn. And because f double prime is continuous, this is roughly equal to 1/2 f double prime of xn over f prime of xn times epsilon n squared. And again, you can make this rigorous by considering this minus f prime of xn plus f prime of xn. You can make this rigorous just by considering, difference, right? By adding and subtracting f double prime of xn. I'm not going to do that. We have better things to do. And the point is, this is, so I guess epsilon comes that, yeah. And this just becomes m, so it's less than or equal to m. And so the whole thing is less or equal to m times epsilon n squared. So I have shown, again, a bit of a hand wavy at the end, but if xn is close enough to x star, then in fact the error becomes quadratic. So in particular, if this error is very small, the next error is small squared, which is even smaller. So it's a pretty efficient method, and I think that's how people use it in general to find roots of polynomials. And there are better ways, I think, but as I said, this is not my field, so I'm more PDs, pure PDs, so I'm like at the dark side or something. Alright, so if you like that and you want to see more math, please make sure to subscribe to my channel. Thank you very much.